I'm going to talk about some, I guess, explorations into the concept of work here. It's a lot less universal than what Eddie was just talking about. We're not trying to find the quantum state of the universe. We're trying to figure out what like the concept of work is, or like this debate in quantum thermodynamics recently about what work is, or like how do we define work. Like Eddie's discussion kind of assumed there's this maybe it's like macro states, right? And then we have like micro states, and then work, it seems to be a macro state. And now I'm like, okay, how do we find that? Right. So it's a very local project. And what I'm interested in is a particular kind of conceptual project in QTD, quantum thermodynamics. So this one Myrvold et al. Calls the challenge of consistently redefining the usual thermodynamic variables, heat, work, temperature, or even reformulating the laws of thermodynamics to make them applicable to systems which are not macroscopic, but fully quantum. And I guess this questions about, what it takes for this project to succeed will probably come out along the way, right? So as Myrvold says, et al. Says, these questions are far from settled and continue to motivate vibrant activity. So Jasinski et al. Notes the absence, at least in 2015, and I'm pretty sure still now, like the absence of a broadly agreed upon textbook definition of quantum work. Tolkien and Hengy in 2016 say that there is an urgent need for a theoretical foundation for what work means in quantum mechanics and how it can be defined in an operational way. And Lostagio 2018 identifies this as one of the main challenges in generalizing classical thermodynamic and statistical mechanical results to distinctively quantum processes containing quantum coherence. So the question is like, our question will be, well, what does it mean to generalize to states with quantum coherence? What will it take for it to succeed? And have we already succeeded in a sense? And that kind of question. Right. So this is a case of quantum work. So some of these conceptual worries, which will be part of the focus of the first half of the talk today, are made precise by a 2017 paper by Perrin Lobert and al. Hope I pronounce it correctly. So they proved this no-go theorem, which I'll just call NGT for ease of pronunciation, that's supposed to rule out a universal definition of quantum work, in a sense of universal that we'll come to see. And they do so by showing the inconsistency of a measurement scheme, and I'll clarify what that means later as well, that satisfies two conditions. And these conditions stem from the roles played by the classical work concept, or so I claim or try to diagnose. So Pinto Silva and Galweza Klimowski, sorry, I butchered that pronunciation. Remarkably, they say, there's still no statistical framework for describing work that aligns with the NGT's conditions, suggesting incompatibility between quantum mechanics, convergence to the classical limit, and thermodynamics. Things which will be, I guess, devastating in a way if somehow our best fundamental theory of matter could not be put together with our best sort of theory of macroscopic world. The worry there. But ultimately, the worry is very local once we see it. Right? So what I'll talk about today is I'll introduce NGT, two conditions generalized from two classical roles of the work concept, which I'll just call unitary and TPM, two-point measurement, which is the standard, I guess, by now sort of standard scheme for measuring work in the quantum domain. And then I'll provide a diagnosis of the NGT, and unsurprisingly, it's got to do with the measurement problem, I think. Right? And then it raises a question of what we mean by universal, right? When we say we want a universal concept, but we want it in terms of measurement schemes, is that how can we make that universal? And I'll talk about the role of decoherence and interaction, and how that plays into this theorem, and how I think it might temper some of the worst sort of upshots of the theorem. And point out that in some sense, classical work concept, maybe unsurprisingly as well, still falls apart in a way they'll make clear. So maybe things fall apart, like my thing, right? So the second half of the talk will then say, okay, what if we wanted to go further, right? Search for a different kind of universality. And I talk about quantum force. Quantum force is defined in terms of frameworks that uses a quantum potential. Bohmian mechanics is the most prominent one, but something like a many interacting worlds framework that, say, Chip Seaburns have developed in 2015, that would also have a potential. It will mean different things, but the potential can still be used to define a force, in terms of which you can talk about forces over trajectories and then define work. So I'll compare that with Sampaio et al.'s 2018 proposal, which also uses the Bohmian framework to define work, and kind of say how our concepts are definitely related, but not exactly the same, extensionally speaking. Right? And this provides a different sense of universality and resolves the original breakdown consilience that sort of arose because of the NGT's diagnosis of the situation. But the bump in the rug is merely moved to another part of the carpet, I guess, not fully removed. And then the open question is something I need to remove this first. Open question is what counts as a working work concept? What works for us? Right, and that's a question I have not solved yet, and this is something we can talk about in the Q&A. And then you click here. So moving on, I'll just briefly talk about the constituents of the classical work concept. I assume most people in the audience are familiar with what work is. Right, so I'll just kind of refresh my memory a little bit. I can talk more about this. I had slides, but I decided to cut them out. So yeah, what is the classical work, right? And in what sense is it consilience? In the sense I'm using the word consilience, I simply mean that there are many distinct ways, not necessarily independent, but distinct physical ways of defining a single concept, providing it rich physical meaning, right? So in the case of work, in the right regimes, the classical thermodynamic regimes, these perspectives are intertranslatable in and close to around equilibrium, giving rich meaning to the concept of work. So on one hand, operationally, and perhaps the earliest way in which work came about is a way to measure the amount of quantity of mechanical effects. People like, I guess Galileo had a definition in terms of power, force over velocity. Right? Perrin uses force over velocity in the early 1700s, and then Smeaton, 1759, talks about force in terms of, work. Right? He calls it power, but he defines it as work over force over distance. Right? And he says time is just a measure of that thing. Right? So it's not really crucial to the definition of the mechanical effect that we think about time. We just think about force over distance, and then we can compute it over time as well. So that sort of talks about both the operational and forceful, I guess, perspective, right? The net force acting on the system over distances, where you have, if this works, yeah. So you have today we'll have a contemporary definition in terms of forces over distances, force dot the displacement, and integrate over that along a trajectory, right? That's the most sort of standard textbook definition of work. And of course, we can connect this to energy, right? As a change in kinetic or total energy along a process, right? This is called the work energy theorem. This developed out of the combination of work with this operational and force notion of work with the energy notion of work came about a bit later, right? As a result of the vis-viva debate where you talked about, well, what's the quantity of force in the system? Is it mv or is it mv squared? And then eventually people like Senior Carnot will have provided a sort of numerical equivalence of work and energy. And then Coriolis in like the 1850s, I think, or 1820s, combined them and said that they are conceptually the same. And Coriolis says something like people would think of the living force as a measure of quantity of the force is like mistaken. Today, everyone agrees that it is work, right? And that's like back in the 1800s. So work and energy was already sort of conceptually connected back then. The change in kinetic energy specifically. But later on, we can generalize it by considering internal, external force work done. And then we think internal work is a result of conservative forces of the form, like, I guess it's number, but it's a total change in potential, right? And the external work is just coming from the outside. We can talk about generalized work, right? Moving this to the other side, we say the external work done is the amount of work required to effect some amount of kinetic energy change while overcoming some amount of potential energy as well. And then thermodynamically, along the same time as well, people are trying to find connections between the mechanical effect, i.e. work, and heat, right? And that's something that also talked about by, say, Thomson with a P, and then there's von Meyer, and then there's Joule, and then there's like Lord Kelvin and Clausius, right? These people are all connecting work to heat in appropriate sorts of processes. And out of that came this other notion of work, right? First law of thermodynamics, right? You connect thermodynamic work to thermodynamic heat in terms of this conserved quantity called the internal energy. Because the caveat is that internal energy is defined only in or approximately in thermodynamic equilibrium, right? It's a state parameter. You can only break this dq and duw into smaller parameters if you are in that right regime, right? So it's a bit tricky to look at identity like this, right? There's a bit of caveats about when you can use the first law and when you can't necessarily. So this leads to the last question, I guess a more recent question, right? Which the topic of many the talks today, which is the statistical approach, right? Where broadly I'm going to talk in terms of Gibbsian ways, just not because I'm Gibbsian, but because this is just how most of the practice is proceeded, right? So you start the Hamiltonian, you find a way to separate it separate the potential into external parameters and internal parameters. And then you say work done is just a variation of the external parameter of the Hamiltonian in appropriate closed situation, right? And then you can define this variation of a Hamiltonian with respect to the external parameters, and you get this thing. You just call it A, it's just the work, right? Well, it looks like a work. And then you get this total differential that looks a bit like the first law. If you're willing to accept that S here, which is the Gibbs entropy, is the entropy or the thermodynamic entropy, or some analog of it, which is what Gibbs would say, right? The analogy of the first law. He wouldn't say it is the first law, he says it's kind of an analogy to the first law. And then here, if you're willing to accept that these are all the sum of possible work, I guess thermodynamic work that you can do on the system in appropriate regimes, say quasi-static processes, then you can connect work this way to the temperature and the entropy and the heat via this way, and then get a kind of statistical first law. And again, it only equates to the first law, the thermodynamic first law in the appropriate regime, say thermodynamic limit. And of course, it's only in terms of expectation values. And then the rest of the workshop, I think a lot of talks will be, what are these? How do we interpret this? We're going to set that aside here, right? We say empirically, we see like long runs of experiments, and then we get some averages, and that's kind of what we're talking about. Of course, you can ask a good question: what is probability here, and why should we expect this to be equal to this in some physical way and not just a mathematical? And finally, we've talked about how you start from the bottom up, statistical mechanics of particles, build upwards to the first law. But you can also start from thermodynamics to ask, okay, what do thermodynamics constrain when it comes to, what does it constrain when it comes to the micro trajectories? And then something like Jasinski's equality, or more broadly fluctuation theorems, will tell you how, say, thermodynamic properties like the free energy constrains the sort of distributions or statistical properties of micro trajectory level work. The expectation value. So the average exponentiated work here is a mouthful, is equal to the exponential of exponentiated free energy. It's a broad overview, right? So the point is that I call these concepts constituent because they're defined in these distinct ways, but we are able to look at them from different ways, provided we are aware of how we're looking at them, in what context we're looking at them, right? And in those contexts, we are able to look at them from, like, let's say, the 5 different ways, and there is no issue, right? This is a very rich physical concept, providing evidence for unified concept work, at least in the thermodynamic regime or something close to it. So this lens is useful for tracking conceptual change, as I propose, right? You find a way that you can define a concept in the domain where you think the concept is as real as it gets. Say the work, right? Like we do work all the time, right? And the heat is produced all the time, right? And you ask the extent to which these procedures, suitably generalized, still agree or converge to each other in the right sort of context. And then you ask, in what domains do they break down? In those cases, do suitable generalizations of these procedures stop making sense, or do they fail to be consistent with each other? And then what to do then? We'll come back to this at the end. Right. So I think this is in line with sort of conceptual analysis, but it's not really conceptual in the sort of intuition-based way, or like what I think the word should mean. It's more like, something like Hartree did a bit of this on the classical relativistic mass in '73. Mark Wilson has done a bunch of work on the force. I've done a bit of this stuff when it comes to special relativity and temperature, and general relativity and temperature just got published, accepted recently. And then I think Billy Brash's group and Nicole Halpin's group there also did something recently when it comes to entropy. They talked about how the entropy, which was at Wayne's workshop last year, right? There is 3 different ways of defining entropy. Usually they're the same in the classical context. And then when we generalize to non-commutative QTD, where the charges are non-commuted or not necessarily commuting, then we see that these notions break apart. And then the question is like, what to do then, right? There's no way to recover the full physical meaning of the classical concept. What do you do, right? It's an open question, right? And these are questions for practitioners to think about. I want to at least point out that there is this like sort of situation there. All right, so without further ado, I'm going to move on to talk about, I guess, what I'm doing today, which is the concept of work in quantum mechanics, right? How the consilience is analyzed there. So to do so, I'll introduce the no-go theorem for quantum work, right? So what is the setup here? It's a paper by mentioned in PRL by Pranav Loba and his team, or like the collaborators. So the setup is simple. You just consider a closed system, a classically closed system with a quantum state rho and initial Hamiltonian H hat. I'm not going to pronounce the hat. So undergoes this state or this system undergoes some process, which can be seen of as depending on the initial Hamiltonian, some unitary evolution, and the final Hamiltonian, which may not be the same as the initial one. Right, so basically, and also it's this unitary evolution takes place under externally driven conditions. So you're changing the external potential in some ways, tuning it, and then causing the Hamiltonian to change along the unitary process. Right. So Perron-Lobert et al. Say, given this process, there are several approaches to obtaining the statistics of work. Right, that's not surprising, maybe because of the consilience of the work concept. So but when they say statistics, they mean the set of measurement outcomes, W, and their probability distribution, PW, which is kind of related to, we will see, like POVMs that Eddie was talking about just. But they say, oh, there's several approaches, but this is supposed to be a problem, right? Because, and then they say, unlike in classical mechanics, in order to build PW in quantum mechanics, the distribution over possible outcomes, one has to specify the measurement scheme through which this knowledge is obtained. Maybe related to the positivism that we talked about. I call it operationalism here, but maybe it's actually positivism. Maybe I just got the word wrong, right? But I think the idea is the same, right? So to define a physical concept is to introduce some observable as a physical quantity. In turn, to do so is to provide a measurement scheme for that quantity. So to define a physical concept, say work, is to provide a measurement scheme for work, so that, now I know what it is, physically speaking, is the set of possible outcomes with some probability distribution of it. And measurement scheme is simply a set of possible outcomes with a rule for assigning probability to them. And I think the important thing that maybe is underplayed in this paper for whatever reason is that there's a physical realization of the measurement that must be provided, right? And how these apparatus pointer states correlate to the target system in the right way, right? That's what measurement is. Measurement is taken seriously as a physical process. This is what Bush et al. I think in 2009 talks about, right? The measurement theory of quantum mechanics. To put coarsely, I think it's what I call operationalism here again, could be positivism, right? A concept is physical only if one can specify how to measure it. And the broad approach is in terms of POVM, finding a POVM for work, comprising positive operators, MW, each of which corresponds to a measured value of W of work due to the system undergoing a process high. The probability of measuring a system doing some work W is given by the Born rule, the POVM version of Born rule, which Eddie introduced just now, trace rho H or trace rho operator, right? Which is right here, actually. Yeah. Right. With which we can define an expected measured work for any system. And the goal is to find an expected work operator, which gives us the expected work done for a system in any arbitrary state. And this is kind of what he means by universal, what they mean by universal, right? It means state independent. So if I have the idea is that if I have a POVM, doesn't matter what state you give me, it's gonna get outcomes that corresponds to at least one of the outcomes in the POVM, right? I don't have to think about what the initial state is, so I don't have to tune the measurement apparatus, I see here, to the initial state, right? They want to kind of universal in the sense that any system passing through this measurement setup gets measured. I guess the idea is something like, a classical example, maybe Sengalak, I'm not sure, like a system passing through it gets spin up or down regardless, provided it has I guess if, yeah, so you can do that. And given that, they specify two desiderata for such a scheme, and they say, okay, if there is such a universal scheme, it must satisfy these two conditions consistently. And these two desiderata, as I propose, are generalizations, which they implicitly and somewhat explicitly talk about too. They are generalizations of two classical roles of the work concept that was played theoretically by the work concept. There's this energetic role, which I talked about, work energy theorem. Also the operational role, which is related to what you can know given that it has some energy. And the upshot of the NGT is that both desiderata cannot be true together. So the first desideratum is the unitary condition, which is that in a closed quantum system, the difference of average internal work, and energy corresponds to the work done. And they say that this goes back to the very definition of work at heat in phenomenological thermodynamics, in which for closed quantum systems, every change of energy comes in the form of work. That is the paper. I think there's a bit of a conflation here as well, because on one hand, you can talk about the first law, and you can say conservation of energy in that sense. But I can talk about the work energy theorem, which holds whether or not you're thinking about thermodynamics at all, right? It's just, at least in classical cases, kinetic energy change equals to net work done. That has nothing to do per se with thermodynamic equilibrium, right? You have not assumed equilibrium, you just say, well, whatever it is, whatever work I do to it, that work is equals to the change of kinetic energy in the mechanical system. Right? So there's a bit of a conflation here. And because the whole paper doesn't really talk about thermodynamic conditions, I'm assuming they're actually assuming the work energy theorem, not the the first law, which of course are related, but it's a bit subtle. So the work energy theorem tells us classically, if a system is closed, then the difference in the system energy as it evolves under classical Hamiltonian is equal to equivalent to the work done on that system. Then maybe using correspondence principle reasoning, we can say the natural generalization, you plug in expectation values instead of the observables, and then you get work done equals to expected work done equals to expected energy in the final energy minus the expected initial energy. You get the trace rule, and then you get this result. So this is the condition, right? So the condition is that the expected work should satisfy this relation here, right? So that the energy, initial energy minus the time evolution energy. Right. This is in the Hamiltonian, the Heisenberg representation to make it clear. Right. So the second desideratum, operational, right? The TPM conditional, the condition, the 2-point measurement condition is called TPM. So in classical physics, measurements can be as non-invasive as one once, right? Energy measurements of the system at 2 points in time will give a result arbitrarily close to the actual initial and final energies of the system. And the 2-point measurement scheme operationalizes this practically in quantum mechanics via so-called 2-point projective measurement. So I want to find out the work done in a quantum system. The idea is that I just take the operationalism or the operational procedure I had in classical mechanics, bring it over, right? And Topman et al. In 2007, when I think one of the first people to propose this, they would say, yeah, it's just an elementary observation that 2 energy measurements are required to determine the work performed by a system, on a system by an external force. So I measure it once, collapse it to some eigenstate, and then let it run unitarily under some external perturbation variation, and then measure it again. And I take the 2 measured values, I minus them, so I take the difference of them and get the work along that run. All right. And then if I want to do the expected work, I just measure it a lot of times, and then I get a distribution, expected value out of that. Or I estimate expected value out of that. The same one precisely, right? The condition is that for states with no quantum coherence, the result of classical stochastic thermodynamics should be recovered. And the key connection is that the TPM scheme was proposed by developed by Jasinski et al. Further, and they show that in this scheme you do recover, in terms of expected work, recover relations that are sort of familiar to classical stochastic thermodynamics, which Pascal will probably talk about more tomorrow, I hope. Yeah. So formally, they demand that this holds, and that the relation is that the expected value, or the probability of some work being done is equal to the trace bond rule of the quantum state with this POVM that they defined here. Right. So the setup is that you have an initial system, initial Hamiltonian with some superposition of eigenstates, energy eigenstates. Right. You do some unitary evolution, and then you get a final result. And then work is the measured result, EF minus EI, the difference, right? And the probability is the transition probability from I to F given the unitary evolution, Bond rule. And then this is a probability of the system initially being in I and then transitioning from I to F. And you get the probability of work done, which is work WIF, which is here, the probability of going from I to F with that energy value. And then the probability of the system doing some work is the sum over all the energy differences that correspond to the same I guess work value being done. And then this is just a generalization of this in terms of the POVM element. So again, expected level wise, it seems like there's no issue per se, right? We get nice results that correspond, as Jasinski showed, to classical stochastic thermodynamics. But then there's the worry here is that, well, what if I want to go beyond that? I want to think about systems in coherent states, which is their goal. The universal means extending to coherent states. Now the proof proceeds swiftly with this in terms of these 2 conditions with a single counterexample. Right, start with a 2-level system in the state rho with some initial Hamiltonian, which they set because this is a counterexample. They just set it to this. Right, initial Hamiltonian is in the 1, so 0 and 1 are the 2 possible levels. 1 is one of the levels, and then it has an eigenvalue E. And then the final one is E prime with the same state, the same level. And then with the interim unitary evolution, where in terms of this I guess a nice superposed unitary operator. And then you can just run it, just calculate it, and you find that, right, with the TPM condition, where you define work in terms of this probability distribution, and you can calculate the transition probability. Given this, the transition probability is just half. from I to F and F to I. It's symmetric here, right? And then you calculate the work done at each point, which you just like, if you initially was measured at 0, and then later measured at 0, what's the difference, and so on and so forth. You get minus E prime, E minus E prime. You plug it in here, right, for the expected work, which is sum over all the possible states with the probabilities given here. You get this term, right? The expected work is the sum of minus half epsilon prime, or the 0, I can see it, I guess, corresponding to 0, I can see it, and epsilon minus half epsilon, E prime, epsilon prime, sorry, for the second level of the energy. So that's the first condition. Second condition, right, you assume what we saw just now, unitary evolution of the system, right? Difference between initial Hamiltonian and then the new Hamiltonian after unitary evolution under external variation. Calculate it again, right? Just plug it in. You get the expected work is this term here because of the superposition of this state here. You can expand it in terms of this in the density matrix formulation. All right, and you get this result. And then, of course, the point, it should be obvious that these two things are not the same. Right? These two things are, or rather, they are not equivalent to each other. So demanding that the TPM conditions hold for what we mean by a work, expected work, gives us this result. Imposing the unitary condition on work done gives us this result. And then they're obviously not the same. So now we have a contradiction. For all non-zero epsilon, they claim, right, the two conditions cannot be true together. Seems like a fairly, it follows straight from simple basic quantum mechanics. So they say then that our results show that two physically necessary properties of quantum work. Firstly, respecting the classical limit obeying the first law of thermodynamics, says the TPM condition cannot be, be simultaneously measured with the obeying of the first law of thermodynamics. So the classical limit being TPM, the first law being unitary condition. And then they say there will probably never be an equivalently universal notion of the work variable that's independent of the context in quantum mechanics. And then the response is also interesting because largely there's been acceptance, right? Agree with the conditional. If the two conditions are true, then no universal concept expected work can be obtained. And then other people mostly, after acceptance comes sort of a revision or how to respond or avoid the issue, right? And by avoiding the issue, some people like say Lostagio will say propose that we just do things in terms of quasi probabilities, perhaps with weak measurements, and then Pinto Silva and Gawarza Klimoski talks about alternative measurement schemes, maybe not the TPM, something else, right? So for the quasi probabilities, I'm suspicious, probably because I just don't, like, it's possibly quasi probabilities are possibly negative, and then there's like questions here. Of course, operationally, you can find a way to make it work. I'm just personally thinking, oh, can we do something else, right? And Potts kind of conclusively say in the review, right, just one of many reviews on quantum thermodynamics, that we do not define a stochastic version of the work associated with the time dependence of the Hamiltonian. The reason for this is that if the initial state doesn't commute with the Hamiltonian, that is, it's not time independent, then there is no unique way to define stochastic work that obeys all desired properties. And they cite Perrenot-Lobez's work. So they're saying that these two conditions are the desired properties. And because of that, we don't get anything. It's impossible to get something that coheres with all of them. So my response is as a philosopher of physics, it's not like step into the nuts and bolts of the experiments, to think about it a bit more conceptually. Because it's not to say this is the only way to think about it. You might think of it much better in some other ways. This is just how I'm thinking about it. I think of it in terms of the measurement problem, right? So to take stock, the NGT tells us that the unitary and TPM conditions cannot be true all at once. If we did, we get W not equals to W, contradiction, right? Anything follows from contradiction, explosion, right? But what the NGT really shows is simply, right, that you define work relative to the unitary condition, which is not equals to the work defined by TPM condition. And the further claim is that these two things are somehow physically equivalent, perhaps in the sense of describing exactly the same system, which we saw just now is the just simple two-level system, right? That's the only thing we care about. And somehow these two ways of looking at the same system gives us a contradiction, right? If we think about that, then we get a contradiction because now we're saying, okay, if I look at the work from this definition, I get extra off-diagonal terms. We look at it from this other definition, I don't get the off-diagonal terms. Contradiction, right? Like what is going on, right? The same concept, same system. But if we think of it as just, expected work for systems in unitary evolution per se, it's not the same, and partially close, it's not the expected work for a system undergoing a TPM scheme, right? The further problem of problematizing the NGT arises if we somehow assume that the two setups are physically equivalent, just two ways of defining the same system and defining the same work for them, And this assumption amounts to a consilience of the two conditions. They are the two different ways of defining one single concept for a single system. They are of course equivalent and like approximately equivalent to arbitrary precision, right, of defining work in classical physics. And they also may be a result of one stripe of, I guess, operationalism or positivism in quantum mechanics, right? That energies at a time is physically equivalent to what we would measure at that time. Then the work done on the system is physically equivalent to the measured work done, right, initially and final. But I think decades, I guess a century now, assuming we started thinking about this the moment quantum mechanics, the Schrodinger equation came off from the mountains, right? Decades, century of work on the measurement problem tells us something different. Right? Broadly, the unitary evolution generically is to superpositions and coherent states. Yet projective measurement outcomes are determinate and do not contain the coherence that we predict with our formalism. The classic example is double slit versus double slit monitoring. So I was thinking, is it just the measurement problem? Right? I think it's a bit simplistic, but this is the framework I'm going with for now. So seeing this way gives us new resources for addressing the NGT, which is why I'm interested in looking at it this way, right? Because the biggest takeaway is that all major approaches, I think, correct me if I'm wrong, would agree that the two conditions take out two physically distinct situations, right? The top one and the bottom one. Presumably, even someone like a hardcore positivist would say, yeah, of course, yeah, the different kind of operations I can do on them, right? So these two are physically distinct. One is a double slit, one is a double slit monitoring, and the behavior, the measured behavior is different, right? But also that another upshot is that measurement brings in, as everyone talks about here in foundations, right, large macroscopic system interacting with the original system with approximately orthogonal pointer states. And this interaction causes collapse, apparent collapse, branching, updating of beliefs. So this raises a question for the search for this universal measurement scheme. Well, I expect to find one for which the expected work for superposed, I guess, coherent states, like the class of counter examples they provide in terms of coherent off-diagonal terms, is exactly the same as the one for TPM measurement outcomes. Now, this is not to say that the two conditions have nothing to do with each other. They're just completely irrelevant to each other. That's not true, right? And by eyeballing the situation, right, a superposed state that is projectively measured in the work base, the basis, I guess in the energy basis here and then energy basis here, would use statistics approximating the TPM's condition. Right? We took projective measurement seriously. Say, once you have the unitary condition and I say, okay, how do I measure it? You bring in systems to measure the energy. Then you just get a universal scheme, right? Because the decoherence, given some appropriate time scale, causes the off-diagonals to approximately vanish. I think all major approaches agree something like this is happening, right? So even for superposed state, there is a universal measurement scheme, right? You just give me a superposed state, tell me what the physics of the measurement device is. Are you making a weak measurement? You're making a projective measurement. Put them together, look at the interaction, and then in lucky cases or in good cases where we have good control over the system, we know what to say, right? For all practical purposes, TPM is universal enough because you can see that once you kill off the off-diagonal terms, it's exactly the same. The expected work is exactly the same, right? If you can kill it off. So the question is, can you kill it off? So for all practical purposes, I think if you think that decoherence solves the problem, then for all practical purposes, TPM is universal enough. And you give me any state, I'll put it through appropriate measurements, like say even a TPM, right? Then I get the expected value, and that's it. Much of the potential of the NGT per se, in terms of measurement scheme, dissipates. But if the worry is instead that we cannot observe the predicted statistics in the superposition or the coherent basis of energy states of genuinely isolated superposed states undergoing unitary evolution without considering measurement devices at all, then no measurement scheme can help because this is not a measurement. There's no measurement going on, right? So how do you get a measurement scheme when measurement seems to be maybe not precluded, but at tension with the kind of states you're trying to look at, right? Because weak measurement can work, but then there's just minimizing the back reaction. So the latter requires a different sort of universality, I think, proposed to people who are not so interested in the foundations, right? Afforded by approaches to the measurement problem. But I don't want to oversell it, right? So the NGT's most worrying implication is that there's no way to reconcile them per se, can be tamed in a sense if we consider the physics of measurement and decoherence. But it remains true that the two operational energetics role do fall apart, partly just because of how quantum mechanics is, right? For some states, they don't tell you what you would measure. You would measure something distinct from what the state actually is, right? You will get the state predicts off-diagonal terms, but you don't get to see those off-diagonal terms, right? This is the measurement problem, in a way of putting it. right? Because of the general invasiveness of measurement in quantum mechanics. So the two roles fall apart in that sense, per se. And furthermore, the orthodox approach to QM that is prevalent, right? There are no trajectories with which we can define forces over trajectory, another role that's played by the classical work concept. So Hofhanniskian and Imperato say here, when information about the full statistics of work is required, especially relevant for small systems, classical mechanics answers by means of trajectories, leaving no prescription for assessing the statistics of work in the quantum regime. So even Jasinski's equality depends on work in the sense that you're evaluating Hamiltonians along some phase-space trajectory and then computing the work done along the trajectory. But there's not, in the orthodox picture anyway, right? It seems, or it depends on what you mean by the orthodox cause. Some people would say, there are no trajectories. Like, it's just when I measure it, I see it, and then when I don't, I don't. So maybe like a Heisenbergian type of, I'm not sure it's exactly Heisenberg's view, but like when you have the lamp and then you shine on it, it's there, but then lamp is off and then nothing until the lamp shines. It's hard to pin down what exactly implicitly is going on here, but this is just my sketch. Senpai et al., who proposes the Bohmian approach, says that quantum mechanics is routinely taught in a way that stresses subjectivity and indeterminism, while abolishing trajectories in phase space. So at least that kind of trajectory is gone. So TPM work statistics obey Jasinski's equality in the sense of work differences, right, but not works along trajectories. What of actual trajectory level work? In orthodox quantum mechanics, there's no such, or at least people don't talk about that kind of thing. So there are no actual forces over actual distances with which you can define work. So that role is just like left to the side, which may be fine. Maybe it's too classical. You're like being you love classical mechanics too much if you want that kind of thing here. But can we try to force it in? Right? Well, I guess we could, right? And we can talk about quantum forces over trajectory. So I'll sketch a framework for the rest of the talk, so setting the NGT aside for the moment, for defining actual work via the quantum potential, in which the three roles, energetic, operational, and work forces over distance, can be reconciled. Like I said, other non-Bohmian approaches can also define quantum work in this way. For example, Siemens's in a many interacting worlds approach, where I suppose one way of reading is that all these trajectories are there in the world, the real world. They're interacting each other via the quantum potential, and there's no wave function. Right? The wave function is replaced by the density of worlds at a point in a region of the space, configuration space. Yeah. So it represents interval action. I don't say interaction because it's tricky to think about Bohmian potential, as you see, in terms of interaction. And then in Bohmian mechanics, the quantum potential is action of psi on the particle, globally all at once. So the work that can be done in Bohmian mechanics is not prominently discussed in QTE, which is why I thought it would be nice to at least put it on the table and say, hey, this is one way to look at it. The Senpai et al. Is the only exception to my knowledge. I may have missed people, right? If I do, let me know, and then we can see how they match. As some of you may expect, this will just move the bump in the route elsewhere, right? Especially if you are not a fan of Bohmian mechanics, right? You'll find that issues there. I'm not saying this is perfect again, but I do think that constants still breaks down. Even if you had this nice thing, you restored this constants of these three things, you push the bump in the route elsewhere. So just a brief basic formalism for in case people are not familiar, right? Instead of just the wave function of the universe, right? Say Everettian or orthodox quantum mechanics, we also have a configuration, actual configuration of the full set of particles in the universe. At least this is in the non-relativistic quantum mechanical context, or context in which particles make natural sense to introduce, right? So with this wave function, you can decompose it in terms of this the Madelung representation, in terms of a real term and the phase term. And then you postulate that the velocities of Bohmian particles are given by the so-called guidance equation, right? The change of these Bohmian particles, which are these trajectories over time, just is given by the gradient of the phase of the wave function at that point. Oh, and this messed up. Yeah, so assume equivariance of probability distribution so that the set of the ensemble of trajectories is distributed at initial time with respect to the Born rule. And once you fix that, then equivariance guarantees that they always are distributed according to the Born rule, so that the Born rule plus the wave function, if you have no knowledge about the particle at all, is always the best, I guess, epistemically the best guide to knowing the statistics of these particles. So some quick remarks. Only the positions are non-contextual. So connecting back to what the contextualism that Carnal, Lobet, et al. Will worry about. Only positions are non-contextual in the sense of not depending on the wave function at all, the state in that sense, being primitive ontology. It's just, there. The fundamental furniture of the world are these positions, these particle positions. And all the quantities, as you see from the equation here, everything depends, starting from here, I add a psi here to show that, everything starts depending on the wave function. And because the wave function is set up depending on the physical or say sometimes the laboratory constraints or other information you might have about a system, and then that makes it contextual. So it is not universal in that sense. But for the Bohmian perspective, this is a feature, not a bug, since almost everything depends on psi, and then some people want to remove everything from quantum mechanics except positions, right? Say like Esteldian kind of superhumanism. It's a moot point to try to find universality in this sense for any quantity that isn't position or observable about position. But Bohmian mechanics and approaches like this provide a distinct sense of universality, even the Abelian one, right? Has this kind of feature, right? In that there exists a determinate ontology in all contexts, in which NRQM applies, and possibly some context in QFT, right? Modulo worries by David about the Bohmian mechanics, right? So it also reunites the energetic and operational roles in a sense. The always determinate state, which of course, masking into entanglement, interaction, to be filled out depending on the approach you're taking, determines exactly what will be measured. And I particularly want to stick to the quantum Hamilton-Jacobi equation formulation, the second order formulation of Bohmian mechanics, instead of the one that simply postulates this and then done. I mean, in theory, you could just say this is the law, but then you introduce this anyway. You could probably do that, right? So it starts with the quantum Hamilton-Jacobi equation, which is a feature of the phase. And then you get this equation here. I'm mostly borrowing from Holland's presentation, right? Because I like it a lot. It's a really nice, clear presentation of Bohmian mechanics. Right? Stipulate this term here, this thing I'll call the energy, the particle energy, total particle energies relative to psi. The sum of the kinetic energies of each particle, the I particle in the N particle ensemble, with the particle potential V and this Q term. So this is the energy, but it contains an extra term, the quantum potential, which is defined with respect to the Laplacian of the real part of the wave function. Again, sorry for the formatting, but so the QHJ gives us, in terms of Q, what I can call the quantum force, which is here. It follows from, I think it follows from here, and then you get this result here, right? Considering the change in time. So this is just, I think I missed up it's correct. Yeah, the change of momentum over time is the force in classical mechanics. Stipulate that because in the QHJ formulation, you get this term and it looks like this, you stipulate the new generalized second law is this. The quantum force defined in terms of the gradient of V plus Q equals to force, right? And you stipulate that this equals F, right? F equals to m dV dt, where V is the the Bohmian velocity. So it looks formally analogous to the second law in terms of a conservative force, except we interpret Q as also contributing to the particle's potential energy, the classical potential energy and the quantum potential energy summed together is this new potential energy that we should consider. And interestingly, Q is generally non-conservative. So there's a question of like, it looks like one, but is it really a force, right? And like, or is it really the same kind of force as it's not, right? But can we accept this and move on? Yeah, we can, and then we see what happens. Maybe we can't, but we can, and then we see what happens, right? Can it go the distance once we have the force? And I think once you have the force, it's quite easy to go the distance here. Once you have the force at a time acting on each particle, you just integrate over the forces acting over the trajectories of each particle, so that you get the work done on each particle, which comprises of the work done by the classical potential and the work done by the quantum potential. Variations in the quantum potential, right? So equals to work over distance, work dot distance, which is equivalent to power over time, power dot velocity along a time, right? Which I just call P for simplicity. And then for n particles, the total work done is just the total power on each particle. So you just get this simple term. Now you can ask, okay, I have the actual quantum work. This is it, right? It's a simple. Once you have the force, things just follow from it, right? At least intuitively. So maybe we can talk about possible complications later. But you can define the expected work based on that now. Just consider how P is distributed with respect to rho, the wave function, or the Born rule, I guess, the mod chi squared of the wave function. Then the expected power at the time is just this, the integral over the expected power over all space of interest. And the expected work done on a particle is the total expected power over time. And then for all particle, again, just sum it up. You can use the linearity expectation to sum it up that way. At least I think that's the case. If I'm wrong, we can talk about it in the Q&A. In a more realistic setting, encoding uncertainty in terms of statistical mixtures or wave functions, you can consider how it's expected wave distributed, not with respect to psi per se, but with over a classical probability distribution over possible wave functions that we're interested in. So maybe connected to Eddie's talk just now. So connection to Sampaio et al.'s Hamiltonian representation. So they define work as well in the Bohmian setting, but they opt to work in terms of the total generalized Hamiltonian, which I've talked about just now, kinetic energy plus classical potential plus quantum potential. And they say, oh, work is just the total change in this energy over time, right? Isn't it just like analogous to the classical work energy theorem, right? The generalized one, where it's just total change of energy, including potential and kinetic energy at a time, from a time to another. And the question is, how does this connect to what I'm saying? This is all about energy. All I'm talking about is force, right? Well, you can see, it can be shown in a special case, like so, right? Take the energy and consider the variation in time. You just like state all these terms, and then you show that this, just by canceling all the m's, you get this term here, right? Which is exactly the power, the force dot velocity. And the change in the variation in potential, variation in quantum potential, get this term. And then if you think for some reason that, because Sampaio talked about closed systems, right? But when we mean closed, if you mean closed as in kill off all the potentials, in the sense of killing off the classical potential and the quantum potential, then you just get the total, the change of energy over time just is the total power acting on the system over time. Sum up over all the particles. And then you get this term here, right? So you show that this, once you do it, then the change in power over time just is the change in energy. Sorry, the total power done over time just is the change in energy from one time to another, and you get the equivalence of F and E, right? So in the case of a truly closed system, free of any time-dependent potential, these two are equivalent. Of course, this means exactly that they are not in general equivalent, right? Because in general, the work I've just defined here is just the internal work done on the system. There's the potential that you can add into, and then what they're doing is considering the work done via the forces, I guess, in terms of the change in terms of the kinetic energy, and then the potential, and then the quantum potential. So we chose this, we arrived here, my diagnosis is that we chose the same path from finding work, right? For me, I started with the classical work energy theorem in terms of work, force over distance, and kinetic energy. And now I see how that works in Bohr mechanics. I end up with WE. Whereas they started a generalized work energy theorem, they just started with total energy. And the total energy the generalized work energy theorem. And that tracks how much energy you put in, total external work needed in terms of total energy change to effect some amount of net work done in terms of changes in kinetic energy. So we're kind of looking at it from different perspectives. You might think, of course, it's not much a difference in classical physics. It just depends on what you care about, which part of the system you care about, right? Internal versus external. When I care about total external work needed to effect some amount of work done, net work done on the target system, including overcoming potential energy, or identifying the network done on the system itself. The former maps onto, I think, their WE. Oh, yeah. Whereas the latter, in terms of network, is what I'll map onto to my WF. So just two different ways of looking at things. Classically, it's not really a question of which one is really better. And maybe even in quantum case too, I just want to say that there are two notions you can think about. You want to make more explicit. I think that there is a difference, right, in what they track in quantum physics, and the two roles diverge. The two, I guess, in the sense of general and classical work energy. The incorporates the behavior of Q because it couples to particles in a particularly non-classical way, so that energy change cannot be so easily connected to net work done on the system itself, which be like the generalized work energy theorem and WE. Whereas I think, well, regardless of what that is, because maybe WF is a bit more humble, it just cares about the change in kinetic energy, maybe it's not that big a problem, but I think these are honestly still rough thoughts, and I'm happy to talk about that in the Q&A. Right. So the first problem I think with WE is that, well, I think it's well known, Bohr mechanics particles do not obey classical conservation of energy. That is, T plus V, the kinetic energy plus the classical potential alone is not conserved. Right? Even when V is switched off, i.e. in situations you will consider classically closed, but not truly closed relative to what I was just defining, there will be forces acting on the particles if Q is time dependent, i.e. the wave function itself is time dependent, if the wave function depends on the Hamiltonian. So even when V is switched off, there is a quantum force working on these particles, right, resulting in change in kinetic energy equivalent to the power over time with respect to the quantum potential. WF will track these changes because tell you there's non-zero work happening. But if you look at the level of WE, which is in terms of the total energy, nothing is changing. Right? These are conserved. But what we mean by conserved is that there is a change in the kinetic energy, there is a change in the quantum potential, and they cancel out. Right? But the system itself is changing. Right? Well, you might think that if you're a Bohmian, you think the particles are moving. Right? They're changing with respect to the changing of the quantum potential. So we could, of course, generalize conservation energy to include Q and say, that's the real generalized energy. No one said energy has to be T plus V. I could say T plus V plus Q. But note that Q can change spontaneously even without external work done if we think that external work can only be done via V. Right? So just like leave V alone, Q will sometimes still change. Right? And then things will still move. Right? So things will start spontaneously moving. You can say, well, it's conserved. Maybe that's fine. But at least we want to point out that there is this oddity associated with this work. Second problem, there's an ambiguity about what this work tracks, I think. So they say they're tracking power over time with their prompt, which is what I'm tracking too. But there's ambiguity because if you have in mind the energy must put into varying the external potential to act on the system, then that is not tracked by WE, right? Because classically the work done equals to variation of the circle Hamiltonian as we set up in the perennial Lobert discussion via variation external potential V. I put in some energy equals to the change in V. What I get out is not the change in V. I get the change in V plus change in Q, right? Because the Q depends on V, so V does double work, right? Because the quantum potential generally depends on V as well. So putting in some amount of V gives me a change in V and a change in Q. It's just like, oh, nowhere. So one does work proportional to classical force on the system, to the system, but the work done to actual trajectories is proportional to the quantum force instead, not the classical force, right? So the WE doesn't quite track the amount of energy you must put in to do work. Do the kind of work you care about in the classical in the quantum case. On the other hand, if we mean work and power that actually gets transmitted to the system, I would say it is a bit iffy, but I think it doesn't track it because it doesn't track the changes to the classical the trajectories per se. All that's to say it's not tracking the network. But maybe you think, well, that's not what I care about. I care about the total energy, and that's fine. I do think it's a somewhat uncomfortable conceptual space because it doesn't clarify either the energy that must be put in the system to effect some amount of work on the system, nor the amount of network that actually gets done by a system in order to change, or like as a result of the change in its kinetic energy, the mechanical part of it. Right? So it's uncomfortable. Maybe that's not a problem. Like all of I say is just uncomfortable. Maybe not a problem. Bohmians will be sure. Maybe some Bohmians will say, sure, I don't know. So I do think that stepping back from this sort of debate, right? I think honestly it's well, maybe there's some reasons why we want one and one the other. But for both accounts, there is no back reaction, right? For the Bohmian force, a force is not paired with a corresponding counter force, violating Newton's third law, which may be fine if you're okay with that, right? But it is worth pointing out it is violated. And Holland points out this way: particle simply responds to the local value of the field in its vicinity via the potential. There is no reciprocal action of the particle on the wave. Excess energy comes from nowhere, goes nowhere. So it acts nihilo, but not nihil fit. So it comes from nowhere, doesn't go. From nothing comes something. So WF does make it explicit, so maybe it's a plus, I'm not sure. Right, WF makes it explicit because it's explicitly formulated in terms of force acting on the particle, but hey, what about the other one? It's like, there's no such thing, it's zero. Right? There's no change in the wave function as a result of its action on the particle. Another issue is that perhaps there's no clear way to recover exact classical statistical mechanical results at the level of trajectories, contrary to classical trajectories. Because the link between work and classical energy is broken, and the coincidence of work is broken once again, in a different way, like I said, the bump in the route has been moved to now we're talking about the relationship between force and work, and no longer about the operational role of energetics and energetics itself. Right. So Jasinski's equality makes some very foundational assumptions, which are totally fine in the classical case, right? That the work along a trajectory is equals to the change in the Hamiltonian with respect to that parameter which you're perturbing it over time. And then in quasi-static processes, you can assume this, and then you can connect it to the free energy directly. So the work is connected to this, which is connected to the work. The free energy is connected to work this way, right? And then you can prove the equality from this starting point. But in the Bohmian force case, a Bohmian work case, work is done on a system even without variations in classical energy. So this is zero because this age is a classical age, it's not a quantum age. So for now, it's like the appropriate counterpart seems to be this H to the free energy, and this can change even when the variation is not changing. Sorry, even when there's no external variation of the classical kind. Nor does Q, I think, to my knowledge, vanish in the thermodynamic or infinite time limit per se, because there's a caveat there. But to my knowledge, it's not like you can just say, well, take these particles, take a infinite number of them, and then this goes away, right? Not directly. So it goes away in just. So it goes away in some sense, FAPP maybe again. Right? For all operational contacts using Bohm mechanics, we only have access, like I briefly mentioned just now, to the wave function with respect to which we can estimate expectation values for the particle's position, and in principle, emergence of like everything else via Bond's rule and large runs of experiments. At the level of averages, Q's contribution to the expected quantum force vanishes, so that even though Q generally doesn't vanish, the expected quantum force part vanishes, even if the quantum force itself at the level of individual trajectories don't vanish. And then the expected Hamiltonian is also conserved in Bohm mechanics. It's proven in Holland as well. And of course, again, in Holland, we get Ehrenfest's theorem again, unsurprisingly given empirical equivalence of Bohm mechanics to orthodox quantum mechanics. So taking stock again, physically, we get a ontologically perspicuous picture of a quantum system with the Bohmian work. It's contextual, it's state dependent, but it's also universal in this other sense I talked about, in the sense of being applicable to any system with a wave function, observed or unobserved. I can say it has a particle configuration in the appropriate regimes. Right? It reconciles the energetics and operational roles, and it recovers the force over trajectory picture, in a sense, in QTD. But it comes with other costs because this recovery is not complete. It doesn't obviously connect to classical stochastic thermodynamics. So you can just take the Bohmian trajectory just is the classical phase-space trajectory. There's something different between these two. Maybe that's fine, right? But then we have to do more work to see how they connect to each other, which I haven't done yet. So this is open question. Not the usual behavior we'll consider part of the work concept because of energy conservation or lack of back reaction. So at the level averages, these costs vanish. But at this level, it's equivalent to TPM work. It's just like you measure and then you measure again, right? So the question is like, how do you pick between these two? If you need to pick between them. So the question is like, the final question, which I'll close off the talk with, does quantum work, right? In what sense does it work? So I was thinking of the conceptual task at hand, and I came across like Mark Wilson's stuff, and I liked it, and so I'm going to quote it here. Right? So Catherine Brading wrote a review of this book, which Mark Wilson himself says is an able summary. So this I'll just borrow from here. Okay. So for Wilson, force itself, classical force, also fragments into several distinct and more precise concepts, each appropriate for its own domain of application. Hertz tried to axiommatize the force, didn't work, right? At least it didn't seem to have explicitly worked. And then mechanics have moved forward, not by unifying these concepts, finding one true work. Instead, we are trying to find different kinds of boundaries for different kinds of applications and different kinds of work as a result, or different kinds of forces as a result. And the means by which we can sort of move across without disaster, which is what I try to show here. Like, you can move across these without disaster per se, right? It's not like there's a one true notion. In distinct modeling domains, general terms like force, and I propose maybe the work as well, specialize to accommodate parochial demands in the sense, non-negative sense of just narrow demands, depending on why you want a work concept for. So if maybe you care about ontology, you want explanation of actual trajectories, I think Bohm and Bohm-like theories are the ones on the market, for now anyway, to my knowledge. And then operational use, TPM works fine and you get all the results you want. So what are we looking for? We look for a universal concept, right? What do you want to get? Well, if you want to recover thermodynamics, so recall this project that Myrvold et al. That started with this quote about reformulating it to make it applicable to fully quantum systems. So if you want full recovery, in the sense of recovering full consilience of all the roles I talked about, I think that the prospects are dim. You're not going to get the full classical work or anything like analogous to the full classical work with all the roles, possibly. But maybe I think that risks taking thermodynamics too seriously. Why expect it to hold in all regimes, including fully quantum coherent regimes? Maybe it can, but if not, would the NGT be so worried? Would TPM work not be enough once we add decoherence or measurements in? So one upshot of the discussion can be framed as such, right? The classical work has little chance of being fully recovered in quantum mechanics. We need to make sure that we set our expectations or set the goals appropriately. And of course, if we're okay with the cost of fragmentation and the price is worth it, right? Say in the Bohmian case, I want to do this, but I know that it's not going to be the same, right? And then the TPM case, I know it's not going to give me trajectory level work. Then the question is why we want it for, what do we want it to be, and to parrot Hessinger a bit, right, for these purposes. What standards of applicability are satisfactory in quantum thermodynamics? So I was speaking to a physicist acquaintance, and he says, "Oh, these are all semantics. I just want to measure it. If I can measure it, that's it. Then maybe just TPM is great. So there's not at least given the problems here. I don't think that's an issue. Maybe there are other issues with TPMs. But if we reject the desire for semantic identity for the word concept, perhaps we can have it all, even if each is less than the original. Finally, if one does find the appeal to FAPP measurement schemes, averages not so satisfactory, maybe one has a drive to work on the measurement problem, and you can pick which path you want, and I'm not going to say which to switch. Right. So thank you for your time, and please contact me for any questions or comments. Oh yeah, Wayne, please go ahead. Wayne, please check. Yeah.
Thank you. This was really good, and I think it raises part of a much bigger question of what has to change when we go from classical thermodynamics to quantum thermodynamics. And can you go back to the slide early on where you talk about the no-go theorem and you put the unitary condition up?
This one?
You had a verbal statement of the unitary condition from the paper.
Unitary condition?
Yeah, there we go.
Yeah.
Yeah, this really struck me. We want for closed quantum systems, every change of energy comes in the form of work. Mm-hmm. This is an interesting sentence because what do we mean in the quantum case in a change of energy? I know what that means when the initial and final state are energy eigenstates, but when it's not an energy eigenstate, there's no such thing as the energy of the state, right? And so I think that this is a sort of the difficulty of having a unitary, a universal concept of work in quantum thermodynamics is connected. Like this, I think this is a major difference between classical and quantum thermodynamics. Classical mechanics, you can always attribute a definite energy to any state and hence a definite energy change and partition it into heat and work. Or maybe you can't always partition it in heat work, but sometimes you can. And in quantum mechanics, if it's not an energy eigenstate, you can always formulate the expectation value of the energy, but that's not the same as saying this is the energy of the state.
Yeah, no, I totally agree, and it's part of my puzzlement was trying to figure out what, because this is like I was asking my Nelly, a colleague here, and I was like, is this like legit? And then she's like, yeah, it's like a fine theorem, everyone agrees with it. I was like, okay, at least everyone accepts it. And I was like, okay, but what's going on here? Like, what's this? Like, what is this condition? And I actually want to say a bit more in that this condition is not really analogous to this condition, right? Because this is about measurement outcomes. But the first one has nothing to do with measurement yet until you put in measurement. So it's like, what do we mean by energy, right? When we say H, do we really mean definite H, or do we mean like a definite value of H, in which case we can talk about measured or like eigenstates? But in general, that's not going to be true, like you said. So yeah, that was trying to figure out what's going on.
Mixture of energy eigenstates, fine, you can talk about difference in energy. And maybe we can accept that is the circumstances in which we can talk about difference in energy.
Yeah.
And only those circumstances.
Yeah, and we should probably put us at the level of expected energy and not like whatever precise energy means. Because precise energy in a weird way is more narrow, or like it's a subset of the expectation, is contrary to the other way of thinking about it in classical mechanics, which is good. Yeah, great point. So were you tracking?
Thanks very much. So one thing that crops up in the case of, for instance, Field's work on mass is the idea that there's indeterminacy here. And in particular, he characterizes that through some idea of partial reference. And I guess so you spoke a bit about the kind of open texturing of work towards the end. And I'm curious as to whether you think, for instance, the claims people were making when they were working in the classical regime were indeterminate between different kinds of work, whether we should just avoid these questions of sort of indeterminacy and focus on the conceptual engineering kind of open texture stuff, or whether you think, because something that is disanalogous perhaps here is you've shown there are some serious problems with certain ways of characterizing work. So whether that selects safe by deference to an optimal conception or something like that, a privileged notion.
Yeah, thanks. That's a good question. I think we had a similar discussion last time I gave a talk in US, but yeah, very similar. Yeah, no, it's a good point. So I guess working backwards, I think that, as I mentioned, there are serious problems in the sense that if you wanted the full meaning of the classical work in the quantum domain, I suspect you're not going to get that. So it's serious in that sense. But neither do you get the classical force in the relativistic context. So I guess it's a problem in some sense, right? It's more, but I'm not sure if it's an issue. But like going further up, right? So back to the classical domain. So instead of saying that the reference is indeterminate, I struggle with this because I don't really know what to say. I want to say that in that regime, there is nothing that can distinguish between these different concepts, right? So the question is, are they the same concept in that regime, in that specific domain with that specific scales? Or are they different concepts that we cannot distinguish empirically or epistemologically, at that level? I don't know what to say, right? It's like, I feel like both would work. In some sense, maybe it's like a metaphysical indeterminacy. It's like the concept there could be one unified concept in that regime, right? There's just one concept. I can say there are like 5 different concepts that somehow we cannot distinguish between because I can intertranslate between them in that regime. And then for the longest time, we thought they were the same concept, and now we all realize, we found a new place where actually they all disagree. So that could be another way to look at it. Or another way to look at it would be start with the one concept, and then say in that regime, it's just one concept. In this new regime, these are new concepts that are related to the old concept in certain ways. And that's like there's a distinct new concept in the new domain that relates to the old concept in specific ways. And these new concepts are not related to each other the same way that the original concept is related to itself. Yeah. Thanks. Great question.
Thank you very much for the very nice talk. First, I wanted to touch on something that was mentioned in the first question, and it's about the difference between the 2 conditions. So I think that one very key difference between them is that asking for the average energy change of the system to be consistent with the average work inquires that you are doing an average. This is not a definition of work that you can do over single trajectories or single realizations of an experiment. Whereas the second condition is more consistent with what we will say is more similar to classical stochastic thermodynamics. So in that sense, they are not equivalent from the beginning. So yes, that condition is not verifiable at the level of single trajectories. However, this also happens in classical stochastic thermodynamics, because if you derive the probability distribution function of work, this one that fulfills fluctuation theorems, then by means of inequalities, you can recover the phenomenological laws of thermodynamics. And these are average laws. And this is like a very nice microscopically driven way to derive phenomenological thermodynamics in a sense. So I think that they are. It's possible to coincide both in the same sense in for quantum systems only if you renounce to having well-behaved probability distribution. That is these quasi-probabilities approaches by Matteo Lostaglio and similar approaches. So one thing that I'm not sure is why. Okay, my question is about having said that about this first part. My question is more about the generality of defining work in the Bohmian framework along trajectories, when it is not in principle possible to find always these trajectories in systems that may have fundamentally contextual features, meaning in the sense of Leggett-Gark inequalities violations and stuff like that. So is it general in that sense? Is it always possible to define these configuration space trajectories along which I can define work? Because I think there are alternative ways to go to trajectories in quantum systems, either looking at trajectories in the Hilbert space in open quantum systems, which require non-Markovianity and secular approximations, but you can actually describe stochastic trajectories in the Hilbert space using quantum trajectories. Or there are also the representations that rely on representing the characteristic function of work as a path integral and identifying a work functional that recovers in the semi-classical limit a power integral notion of work. So yes, I'm not sure about the generality of the Bohmian trajectory, the possibility to define that trajectory.
Yeah, maybe there are like better people in this audience than me to talk about this, but I think that it's general insofar as you can assume that the Bohmian like framework holds, but there are like many limits to the Bohmian framework. Firstly, you need particle representation, and you need precise you need to have the position representation. It's a question about what position means when you go to field theory. It's a question of what particle means when you go to field theory, and then in those cases, there are works being done to generalize Bohmian mechanics to those cases, but I don't think they are. It depends on who you ask, but whether it's complete or incomplete, yeah. So I think it's a good question, and then I actually didn't know about the other two options, so I want to look into them. So maybe we can talk more later and can see what to be helpful.
Thank you.
Yeah, thank you.
Thanks. I mean, this was just a thought as to why, if anything, we might care about finding a notion. I mean, for me, one starting point goes back to the quote you had at the beginning as to what the goal was, where I forget who you were quoting, but the idea was somehow we wanted to move from the macroscopic characterization to the quantum characterization. Now, it seems to me that conflates two things. That's not a criticism of you, obviously, that you're just quoting. I mean, we have a macroscopic kind of characterization of systems and in terms of thermal expectation values or whatever. And we can think that way classically, and to some extent we can think that way quantumly. Classically, we can definitely also think at a microscopic level. And that's exactly the level at which something like Jasinski's equality is developed. It's absolutely a result about a microscopic definition of work that's totally microscopic but classical, which generates these results that generalize standard thermodynamic results. Now, from that point of view, the question is like, what can we get out of quantum mechanics that lets us generalize those sort of ideas? And to some extent, the answer might be like an inchoate mess. That's entirely plausible. But at the very least, we'd like to be able to understand from that inchoate mess why it is that these classical descriptions work. I mean, the classical Jasinski equality is a beautiful result about a regime that doesn't strictly exist, in the sense that there is not that regime of microphysical trajectories sharply defined for individual atoms that's presupposed in the result. The quantum version of the Jasinski equality is perfectly cleanly defined, but its interpretation is hid in darkness. The thing I at least would like to get from this is some way of understanding the conceptual content of these things that kind of legitimates what's going on in the classical Jasinski derivation and shows how it's linked to some story or other at the quantum level.
Mm.
I mean, it would be weird if there was just no. I mean, sometimes life's weird, but it would be weird if there was just no way of legitimating in some appropriate regime the Jasinski account of the sort of the classical arguments in the Jasinski equality.
Yeah, no, that's a good point. So I guess the point is that, well, can we find something that explains the classical? And question is like, is something like the TPM like approach good enough for explaining that? Like that, things measured at one point and measured at another point has connected or separated by some distance. You can think about the system changing over that. But I couldn't think of it precisely that way.
I mean, it feels like it isn't, in the sense that, I mean, this is inchoate. I don't claim this is a rigorous argument, but I mean, the classical Jasinski equality proves a extremely powerful and empirically confirmed result by averaging over sharp classical trajectories for individual atoms. Those trajectories do not exist, and yet the result works. And I don't see the TPM result in itself telling me why it worked.
Yeah.
I mean, maybe that's just I haven't thought about it carefully enough. But that's my entry point to the puzzle here.
No, that's good point. And I've been thinking about it too. I don't have a fully formed answer here. I see the TPM scheme part as a safe point. Like, it's just like, like whatever happens at the TPM level, we get back JE, the Jasinski equation, even go up. Then can we further explain that? But from the perspective of measurement schemes, I'm not sure how far we can go from there, right? And maybe when you go further, then I think that's where foundations quantum mechanics might come in. And then it depends on what you mean by the micro description.
Yeah.
So the Bohmian case, I try to sort of work it out. In the Everettian case, would it just be all the trajectories? Like, how would it work?
I don't know. Yeah. I mean, for obvious reasons, I'm not super sympathetic to the Bohmian route to do it, but I see the itch. Yeah, so it gives you the thing you'd like.
Yeah. I guess I'm not sure what you think about Chip's many interacting walls picture, but then there, it's like in some sense, a position representation of the many walls theory. And then there you get a quantum potential, and then the potential interacts between walls. So like my state of standing here, well, okay, that's not like the precise positions are interacting with other precise position across walls. And that seems to also give you a quantum force, and then it gives you trajectories, all possible trajectories. And those are interacting with each other. Then I think we'll get something similar to what is defined here, because formally they're very similar. Then the question is, like, is that explanatory or not? I don't know. Like, depends on whether you like it or not, right? If you stick to the Everettian level, the pure the wave function level, then maybe, like, I'm not sure. Yeah, maybe not. If we want trajectories, then we put position representation, and we say, oh, there are trajectories, but now the weirdness comes up again, and then we don't get the full work, but we get a work-like term.
Yeah.
Is that enough? And I honestly don't know. Like, it's like, is it enough for us, or is it not?
Yeah, I don't know. I'm very skeptical in unitary quantum mechanics that the position representation is going to be the way to go, just because there's absolutely no reason the Hamiltonian should be diagonalized in it. But it's not like I have a positive alternative to offer.
Yeah. All right. Thanks. You actually can use my mic. Yeah. Yeah. Go ahead.
Well, I have two remarks to make. Maybe kind of superficial, but I don't know. My thoughts go back to the middle of the 19th century, when thermodynamics just got started. When it was realized that Carnot had been working in the caloric theory, in which heat was a substance. And after the experiments of Joule, it was realized that simply doesn't hold. Heat is not a substance, and work is also not a substance. So in later terminology, that means they are not state quantities. You can't talk about a state and say how much work there is in that state or how much heat there is in the state. You can't also not talk about give me an initial state and a final state, and I'll tell you how much work there is needed to get from how much work is being spent by going from one to the other, or how much heat you have to put into the system to go from one state to the other, because it all depends on the process. It's not just a difference that you can calculate by looking at how much work or heat there is in the initial state and in the final state. And this analysis that you brought to us so far seems to rhyme with that original situation. You can get different results in different consequences. So I'm not sure if how deep this is, how close the analogy goes, but I was struck by that. The second remark I wanted to make is I'm also reminded of the fact that, I mean, you have the Bohmian interpretation of quantum mechanics, or Bohmian mechanics. And sure, the addition of this set of trajectories that Bohm has given to quantum mechanics gives it a determinate ontology, which is no longer subjective or indeterminate. But one of the prices you have to pay is, of course, that the choice of the description, the choice of prescription for these trajectories is rather conventional. There are different choices. And even without going to quantum field theory, I remember, I'm not sure who did that at the time, it's a long time ago. You can consider asking the question, well, what if I consider particles with spin? And then you have to replace the Schrödinger equation by the Pauli equation. And then there is also additional terms that can show up in the trajectories. And the choice of the trajectories is not necessarily unique. And rather famously, in one of the approaches developed in this context, you know, in Bohm's case, the striking example was always that an electron in the ground state of the hydrogen atom would be at rest. And in this alternative approach with the Pauli equation, it is still moving in a circular trajectory, just like the classical system would. So in the context of the Bohmian mechanics, precisely because these trajectories are unobservable, there are different choices of prescribing this type of determinate ontology underlying the theory. And I wonder how much difference that would bring to the possible definitions of work that you propose in the Bohmian context.
Yeah, thanks. Thanks for the questions. They're great questions. I think let's start with the first one, which is about
there are people in the context of classical thermodynamics who said that no, you shouldn't talk of heat or work at all, because that closely reducing a noun already seems to presuppose that there is a substance. And especially Truesdale argued that you should only talk about heat-king and work-king as a verb. And I thought from your abstract that you were going to do something in the same direction, but I didn't hear that.
Yeah, like the scope of the project exploded, so I had to cut myself off to make it in time for this talk. But no, these are great points. I agree. Heat and work are process-dependent quantities, right? So they are not generally state quantities, like you said. Of course, in special cases, they can be state independent, state quantities, right? Depending only on the initial and final state. For example, if the force is conservative, right, then and there's a mechanical work, it's not even the thermodynamic. Yeah. Yeah, so I think in these cases, I think they have something like that in mind, where it's like, oh, it's just closed, nothing is happening, and then we assume forces or potentials are scalar potentials, and then we take the gradient like normal. Of course, when you introduce a Bohm case and say, okay, actually, if you wanted to fill in the trajectories, this is what you would get. You would get the Q term just by looking at it in the positions representation, separating out the wave function. You get it. It's in the Schrodinger equation, as Basil Healy would say. Then in that case, it's not unclear whether we are still allowed to take this initial final sort of description, right? Because the force is non-conservative in general, depending on which wave function you use. Like you said, like maybe not directly what you said, but the wave function, choosing the wave function determines how things go from one state to another in the Bohmian case. And then the process matters too, and the work would change because the Q would change depending on how time dependent the wave function is. So I totally agree there. And I tried to like sort of take it at face value here, because I think at some points I mentioned, oh, it's non-conservative, but I didn't really sort of develop it more. I think that's also an issue that the force, even though it formally looks like a grad of the scalar potential, is a scalar potential, is not necessarily conservative because of the way the Bohmian potential, the quantum potential is.
That's also an interesting point, though, because in many contexts, many textbooks that I've seen, force is conservative if it's gradient of potential. That's almost the definition.
Yeah, but that's say it's at a point you take a closed loop, you go back to the initial point, it's the same. But in this case, depending on how you do it, the quantum potential will change in different ways. And yeah, because of the wave function. Yeah, so that's where it's weird. And I think Holland 1988 has an simple example of that. I can't pull it out right now. But yeah, so it's an example. That's what I was thinking too. I was like, oh, scalar means conservative. I was like, wait, is it really conservative? And then Holland says at multiple points, and I read other places where they say, yeah, it's not conservative. I was like, yeah, it makes sense that it's not conservative, but it's still scalar. So it might be something to do with the reason why it's scalar as opposed to being scalar. So it's like a previous work in pressure. I gave a talk last year at Wayne's workshop where pressure is scalar, but it's not really scalar in the same sense that a matter field or mass field is scalar, because the scalar in equilibrium generally is going to be vectorial. If you take a more general fluid dynamic picture of the stresses, it's generally not going to be scalar. But it's scalar in some sense. So maybe there's something, I'm not sure what the reason is, but it might be scalar for a reason, and the reason is usually eluded or like elided because of textbooks. Yeah, so I'm not sure. But that's a good question. So second question. Yeah. The conventionality of trajectories. I would say, I guess, if you say you compare a wave function without spin, and then you say, oh, okay, it's different, trajectory is different from if you put spin in. Is that a convention, or is it just, well, if the system has spin, then I need to find a way to describe it appropriately or empirically, and then maybe I have to put spin. I think it's still true that depending on putting in spin, you can choose how to represent the state, but I'm not sure. Oh, Wayne has a...
About spin. There's conventional choices in constructing a Bohmian theory. So
yeah,
you have the guidance equation, right? And then you can always add a divergence free term to that if you get different velocities.
Yeah.
So I mean, there's a sense in which the Bohmians say, okay, if you're gonna have a trajectory theory, this is the simplest choice.
Yeah.
Right.
Yeah.
But there are conventional choices.
Yeah, no, I agree, and that's something I kind of left off. Simplicity, but maybe simplicity is a guiding epistemic principle too. But I guess it's our law. The Bohmians can say this is the law, and I'm going to say that's the simplest representation. I agree that there's the element of conventionality in how you choose it. I suppose you can quotient out all the equivalent trajectories in some sense if you knew what sort of gauges you're taking. But yeah, that would I haven't want to look at it. Yeah. Yeah, that's a good point, and then you look into it. But yeah, we'll talk more later. Thanks. Oh, we have time. Oh, I think I
do we have time for one more? It's fine if we don't.
I'll try because I'm. But where's now? Okay, yeah, just go.
Just go.
Yeah.
All right. So thanks very much. Really interesting and really helpful. Yeah, I have a bunch of questions, but I guess I'll just ask about one of the comments you made about Bohm.
Mhm.
I think my question is coming from, and the like background worry would have something to do with like the difference between a universal and conditional wave function, because I'm thinking that your results might show consilience applied to the universal wave function, but not to the various conditional wave functions that one often defined using Bohm and then one does measurements on.
Mhm.
And I was thinking, I don't know this. And I was speculating that in fact, you probably could reproduce something like the 2017 result using conditional wave functions. At least insofar as fans of Bohm often claim you can reproduce the sort of standard predictions of quantum mechanics using conditional wave functions.
Yeah.
Is it so? So what that would show then is something like there is. So if these speculations are right, the qualification would be something like there is consilience, but only for the universal wave function, not for these many conditional wave functions that a lot of Bohmians take to be physically significant.
Yeah. Yeah, no, that could be interesting. That's kind of a yeah. I was thinking at the level of conditional wave. I just kind of suppressed it because you're thinking about actual systems doing actual things. I don't know what the universal wave function is. So yeah, but there might be a sense in which you can define it for the true unitary evolution of the universe, but not for the subsystems. It's still kind of weird because all the work we care about are being done at the local level. Still bring down consilience at that level. Yeah, that's a good point. Maybe I should emphasize the conditional part of it. Yeah.